Hey, welcome everybody to another Pionix webinar. This time a ChargeBridge webinar. The future is in your hands and we are ready to ship. My name is Robert Leeuw. I'm a technical evangelist at Pionix and engineering manager, and I will do this webinar together with Cornelius Clause, our CTO. Quick intro, who are we? We are Pionix. We're no longer a startup, we're 5 years old. We initiated the LF Energy EVerest project. We are headquartered in the Karlsruhe region in Germany, and we can help any company that is developing charging stations, with designs, with reviewing architectures, with helping with integration of EVerest, customizing EVerest for you, training engineers to work with EVerest, help with requirements. We can help you with hardware development and customizations. We offer a cloud maintenance monitoring solution for companies for charger manufacturers that want to monitor their chargers in the field. And we can help with updates, security, the entire product lifecycle wherever needed. Agenda for today, I will start with a quick intro on high and low level architecture split of charging stations, then a quick look at the challenges of developing your own custom charging station controller. Then Cornelius will take over and talk you guys through ChargeBridge, some reference designs and the benefits of ChargeBridge. And then I will wrap up with the advantage of ChargeBridge and EVerest combined. And then there's an opportunity for Q&A. For people not familiar with Google Meet, there's a Q&A functionality in Google Meet itself. So you can ask questions in the Q&A section of Google Meet, and we will pick those up at the end of the webinar. So if you look at a typical DC charging station, what kind of hardware do we find there? Now, the main component in the charging station is the charging station controller. The main thing it talks to, it is connected to the charging cable in case of a DC charging station that talks to the vehicle, but you will see a safety relay, you will see an isolation monitor, there's power modules, you need to measure the power going into the vehicle, it's connected to the power grid, then it can have some hardware components that are facing the user more, a display, some buttons, maybe a payment terminal or an RFID reader. And then it also probably has a modem that it uses to talk to a CPO, to a charge point management system. Now, a typical DC charging station nowadays has a split between high level and low level. The high level part is typically running Linux. That's responsible for all the high level communication. That contains all the functionality that is super specific for this product. This is also quickly changing. It uses the flexibility of Linux to make it a lot easier to make a charging station. So you can use a file system, you can use a database. All of that is a lot easier than on a microcontroller. The split to the low-level controller that does the real-time operation to the vehicle, so that has all the requirements on the real-time behavior of the PWM signal. It's also responsible for the safety of the entire charging station. So if the Linux crashes, for example, it's the responsibility of the microcontroller to make sure that the charging station is always in a safe state. It also talks, it can talk to the PLC modem. That's sometimes also the Linux. That depends a bit on the architecture. But it is code that should normally be certified for safety. It's code that doesn't really change that much. It is code that is also has very fixed functionality for the PWM signal, and it doesn't change that much compared to the Linux microprocessor. That's where all the changes happen. That's where the user interface is typically controlled. That is where the newer versions of OCP are implemented. That's where energy management is done. So all of that functionality that is changing way more often, that is done in the microprocessor. That's also where there's more memory, more processing power. But you do want to split, because in the end, a microprocessor Linux is really hard to certify for safety. And with a microprocessor with limited code, it's way easier to certify something for safety and make that responsible for the safety of the entire charging station. So it's a typical split that we as Pionix use, but we see that a lot as well from a lot other companies that make DC charging stations in the field as well. Now, if you then look at EVerest, EVerest is an open source charging station software stack. As I already told, we as Pionix initiated the EVerest project. It's a Linux Foundation energy project now, and that solves the high level control. So it does all the software that you run on the Linux. It has all the OSPP versions, so it supports OSP 1.6, 2.0.1, and even 2.1. It has all the vehicle control protocols implemented. So DIN spec, ISO 578-2, -20. Work is happening at the moment on IEEE 2030.1, which is known in the industry as CHAdeMO. It does all the energy management. It has EEBus implemented. It has SunSpec implemented, and more protocols are on the way. It contains a lot of hardware drivers for the normal hardware that we see a lot in charging stations. It's a very configurable modular architecture. For people familiar in cloud software, it really feels like a microservices architecture. There are a lot of small modules talking via MQTT to each other, making this very flexible, and it's very easy to add modules, remove modules that you don't need. It all has an Apache 2.0 license, which means you can use it commercially. There's no requirement to give it back to the community. I mean, we really appreciate if people help with maintenance of EVerest and contribute to the project, but there is no requirement to do so, which other licenses do. The community is really quickly growing. The ecosystem is growing. More and more companies are supporting it. We were at Embedded World 2 weeks ago, my colleagues, and there's a lot of companies that are now already showcasing EVerest on their booths. Companies like Lumacil, TI, a lot of the silicon manufacturers that are now showcasing EVerest on their booths. There's roughly 100,000 plus charging stations in the field at the moment, and that is quickly growing. And these are AC home chargers, AC public, and DC fast chargers. So all of this is possible with EVerest. So EVerest solves the high-level part of a charging station. How do we do the low-level part? That's what we're here for. So if you want to make a charging station, you need a charging station controller. Now, basically, you have two options. Either you make one yourself, or you buy one off the shelf. If you make one yourself, yeah, you had the option to include a Linux SoM, so you don't need to worry about the routing, and the layout of RAM, for example, which is quite tricky to do that correctly. Yeah, you can buy a module that has the PLC modem on it, so you could combine that into a board, but you still need to make it yourself. Now, you could buy something off the shelf that works out of the box, but it needs to fit your use case. It might be over-engineered, it might be missing something. Maybe you want to make something dual socket and you can only buy a single socket board, or you want to make something with 4 sockets and you can only buy a dual socket. How do you then make 2 boards work together as if it's one charging station? If you want to make a specific size of housing and the board doesn't fit, there's all these kind of things that you will run into if you would buy something off the shelf. So making has its advantages. You can make anything super bespoke for yourself, but it's typically a longer time to market. You need to understand electronics, you need to understand manufacturing processes, you need to work you need to understand the development cycles. So if you want to make a board, you first need to make a schematic, you need to make a layout, review that, then you need to make a first layout, then you need to order the board, then you need somebody to put components on the board, then you need to test it, try to get it up and running. If that doesn't work, you need to go back probably to the schema again, fix the schema, fix the layout, make a new board, have somebody put the components on. And if all of this is successful and you're really there where as that far that you're able to put this thing in production, or at least you're able to charge with the vehicle. You need to go to certification. It also means you need to write a low-level code that does the communication to the vehicle and is responsible for safety. So there's quite some work to make one revision, and typically I've rarely seen a PCB. I'm convinced I haven't seen any PCB come out of a cycle like this first time working. Typically need 2, 3, or sometimes even 4 revisions before you have something that can be put into production. And depending on how much you want to pay in each cycle, yeah, this can take between 3 weeks to half a year if you want to go for the cheapest solution and are willing to wait for factories to have time for you to do the work that you need them to do. Yeah, already mentioned, I think, the issues you can run into. Did I miss anything? Now, typical mistakes we've seen specifically for EV charging is problems around the layout for the PLC chip and the PPCP circuitry. Especially the PLC chip, if you're not doing it right, you don't get a good enough signal to noise ratio with the chip, and then you have a really hard time getting a good communication with the vehicle. You will, and maybe in a lab it works, but then if you go into production and you have this in the field and there's other cars charging, there's other equipment that gives a bit of noise on the cable while charging, this could all result in issues in the field that you will not find, that you might have missed early on. And this, yeah, takes an additional round, an additional testing, and every time you need a new layout, it's cycles that can take weeks or months, and this causes longer time to market. We think we can solve this. Cornelius, you take over.
Yep.
Next, and I will move the slides forward.
Okay, just the next slide. Exactly. So this is basically why we created the ChargeBridge module. So it's a really small module, just 46 by 22 millimeters. But despite of its small size, it actually contains everything that you need for a single charging port. So basically, we created this to make it possible for you to have your individual controller design that completely fits all your requirements in terms of like size and connectors and everything for your charger project without going through the hassle of designing everything from scratch and taking all the risks that you would normally take when doing your 100% full own design. And now you can just use a module that solves all the hard stuff for a charger, basically. So next slide. So the ChargeBridge is essentially a complete front end for a single charging port. You can have, of course, multiple ChargeBridges if you have multiple charging ports, and it builds on top of the same high-low architecture split that Robert introduced in the beginning, but brings us to a whole new level. So it does separate all the high-level functionality like OCPP, ISO 15118, energy management, the user interface, and all of those things that are running on Linux, and they are basically a solved problem if you use EVerest, from the low-level functionality, and that is mostly the safety functions that you need for a charging port. Discussed that as well, but also, which is typically not part of this low-level design, all the hardware interfacing actually, and we will look into that in more detail now on the next slide. So regarding the safety functions, it basically implements everything that is required by IEC 6185123. And all the safety functions are, of course, executed locally on the ChargeBridge, so they don't have any dependencies on Linux. It controls all the low-level communication to the car. So on CCS, this is Control Pilot, CPPP, basically. On MCS, this is Charge Enable and ID, and on the Charge GBT, it's like CC12 or SS12, and BCP and PD signals. It also controls the outgoing relays, so basically the last relay before it goes out to the charging cable, because that's the one that's actually safety relevant. It monitors the connector temperatures. That's, for example, in DC, typically the 2 PT1000s in the gun. It monitors the overvoltage according to the IEC 6185123. That's a feature that's missing in a lot of the charging controllers out there, because it's a relatively new requirement that came in end of 23 and now actually becoming mandatory. And it has safety inputs and outputs to connect external safety devices, for example, the isolation monitor or the RCD. So this basically means the Linux system is like not part of the safety certification. You can update the Linux or change it without impacting the system safety. And it also means the Linux system does not necessarily be located physically close to the ChargeBridge and all the devices that belong to the charging port. Next slide. The second part of the feature is what we call the transparent interface tunneling. So ChargeBridge itself has all the interfaces that you typically need to connect all devices that belong to a charge port. So besides like relay and CPPP and all of that, it also has a CAN port, it has RS485 ports, it has GPIOs, it has I2C. Of course, it has the PLC communication that you need for charging. And all of these devices are basically transparently tunneled through Ethernet or USB to the Linux host. And in Linux, they just show up as virtual local ports. So once you connect to a ChargeBridge from your Linux, you will basically just have a CAN port. That's just a local socket CAN device. You can use it with CAN utils or whatever code you already have. Same is true for the serial ports. They're just like dev/dev/tty something, and you can just use them as if they were local ports in Linux, and they're just transparently tunneled over the Ethernet and come out basically on the other end of the ChargeBridge in real hardware. Now, why is that important? It actually reduces the development as well as the long-term maintenance effort quite a bit of all the hardware integration, because you don't need hardware integration in the Linux kernel anymore. You don't need a driver for the CAN port or anything. It's run entirely in user space, so you don't need to fiddle with device tree customization or anything. You can just update to Linux to a new kernel without any dependencies. You can just install a completely different distribution if you like, and it will just work as before. A second benefit of this is that it scales properly with the number of ports. So if you add a second port or a third port or a fourth port, if you have the typical old design, you will eventually run out of interfaces for CAN buses or Modbuses or things like that. And with ChargeBridge, you will get the same amount of interface per port. So if you add 4 ports, you also have 4 CAN buses. You also have like 4 Modbuses to connect like the power meters individually to one RS485 and without the need to share them. It also helps a lot to reduce the wiring complexity. So we've seen a lot of designs, especially in DC, where there are a lot of wires that need manual assembly and everything. And with ChargeBridge, you can have a lot less wires and you can have them a lot shorter. So you can wire up like the installation monitor, the relays, the power meter, everything where the charge port sits, and you just wire it up to the ChargeBridge and then just run a single cable to your Linux computer. And there's no need to run like all the wires long distance through your case. Next slide. Another important aspect, especially if you look at CRA and depending on how you build your architecture in the end, especially if the network cable, for example, leaves the case, we'll look at that in a minute as well. You want to have all the communication secured and authenticated. So ChargeBridge actually implements the WireGuard virtual private network. It's just a WireGuard endpoint. You can use it in server or client mode, depending on the configuration. And if you use it, that means all the traffic from and to the ChargeBridge to your Linux system is strongly encrypted and authenticated. It's based on a peer-to-peer trust model, so no central PKI needed. And you can also run those tunnels directly into, for example, a container, like a Linux namespace, or even into a virtual machine. It works directly with the Linux kernel implementation. So again, you don't need any special drivers on the Linux side to get this up and running. Next slide. Now, if we combine those three things, the local safety controller that basically monitors the charging communication, as well as temperatures and everything, the interface tunneling, which just gives you a bridge from your Linux system to real hardware ports, as well as the secure communication feature between the Linux and the ChargeBridge. If you bring those three together, it basically means that there are zero hardware requirements left for the Linux system. So you don't need a special embedded Linux that has an SPI port with a couple of interrupt pins that are mapped hopefully correctly in your device tree to enable a PLC modem. It just needs a single Ethernet port or a single USB port. And you can run as many charge bridges as you like, basically over a single Ethernet port. You can also then define the actual topology of the charger purely in software. So you can have a charger that has 3 ports, for example, and you can make it look like one charger with 3 ports in OCPP. But you can also make it look like 3 chargers having 1 port each, for example. Like how you assemble your software and your software architecture is entirely disconnected basically from how the hardware looks like. And the Linux system can now literally be anything. So you can still have, of course, your local ARM embedded controller, as many usually have. But you could also, for example, use, I don't know, a panel PC that might already be present in your DC charger where the display is, and just run the charging stack there as well, and just connect from there via Ethernet or USB to the actual ports, because the panel PC doesn't need to have any special interfaces. During development, you can just use your laptop to run the whole stack there and connect via one Ethernet cable to the rest of the charger hardware. You can use 19-inch servers if you like. We'll look at that in a minute as well, or you can put all your charging stack in containers. You can even run it in a virtual machine in the cluster if you like, because there's absolutely no requirement to have any specific hardware on that Linux system. And that is basically what we mean by software-defined charging. So the complete decoupling of what the software architecture looks like and the charging stack and what the hardware looks like. And to make this a bit more clear, I can show you some examples. So think of building a simple AC or DC 2-port charge controller on a single PCB. That's like a very typical application. So you will basically put a Linux SoM on there. And you can see in this example that 2 charge bridges mounted on the PCB. So from a hardware perspective, this looks like, okay, we have one Linux system and it uses 2 USB ports or USB hub to connect to 2 charge bridges. And then all the hardware, like the actual charging cable and the relays and the RCD and whatever there is actually connected to the charge bridge and not directly to the Linux system. And what will this look like from a software perspective? Well, from a software point of view, this is just a Linux system that runs EVerest or any other charging stack, doesn't need to be EVerest. And you will have local devices. You will see a local serial port, you will see a local network interface, a local CAN bus, and you can use those to communicate with the devices attached to it. And on the next slide, the question is, okay, what if you want to build something like that? Maybe you want to run the Linux system in the central cabinet and have like a bunch of dispensers that are actually having the charge bridges. You can build such an architecture by just using the Ethernet instead of the USB. You use standard Ethernet switching. It doesn't need to be like a 1-port to 1-port relation. You can just use one Ethernet port on the Linux and switch to 20 on the other side and connect the charge bridge each. You can even daisy chain them. The Ethernet topology doesn't matter at all because there's an IP layer in between. And then locally on the charge bridges, again, you connect the whole power path and all the hardware. And so the hardware architecture is like completely different from what we've seen before, having like just a single PCB dual port controller. But from a software point of view, this still looks like exactly the same. You still see local ports in Linux, and the software doesn't even know that they are actually coming out 50 meters further down the parking lot and coming out there as a local CAN bus or a local Modbus. Next slide. Now, if you want to scale this even further, think of a parking garage with hundreds or even thousands of really low-cost AC dispensers with a centralized compute. Now, with the AFIR regulations, you still need like full ISO 15118 support on each of them. But if you're installing 2,000 of them, you don't want to have 2,000 Linux computers in each of them just to do that. And you also want to be super flexible to upgrade this installed system to any protocols or standards that might be coming up. So to scale to those huge installations, for example, you may want to use just standard off-the-shelf x86 19-inch rack servers, can be cheap ones, you don't need a lot of compute power, controlling all of these cheap outlets, basically. So if you go to the next slide. So that can be realized with ChargeBridge as well. We have seen several of those topologies where it basically boils down to having a single point of failure. Like if the global compute stops, then the whole parking garage dies, which is of course not really what you want. So with ChargeBridge, you can actually build this in a completely redundant way. So one example would be you run EVerest in a virtual machine that actually runs in a cluster, for example, Proxmox, in high availability mode. So in case one of your computers fail, the virtual machine will basically just be transferred to another one, and the whole thing will still be working. Now, if we go further to the right, the Ethernet fabric, basically, that's kind of a solved problem. You can build this in a redundant way. That's usually the case in all data centers, so that's nothing new. And then you connect to the charge bridges to have like a fully redundant system where basically each of the nodes can fail and your parking garage will still charge. Now, again, a completely different hardware architecture and a completely different product. But from a software point of view, this still looks exactly the same as the 2-port single PCB charge controller that we looked at the beginning. And this is kind of the idea behind like software-defined charging. You can build your software stack and you can build your hardware stack, but you can do this completely independent and you can rearrange the hardware to whatever your needs are in the future without changing the software stack and the other way around. Okay, so next slide. Another quite important feature, especially for DC controllers, is that ChargeBridge is a whole family. It's not just a single module. It comes in a lot of different flavors for all the different charging standards. And they are all pin-to-pin compatible because all the functionality for that specific charging standard, for example, CCS or MCS, is fully contained on the module. So they are all like single 3.3 volt supply, for example. And if the CCS needs plus minus 12 volt, that's generated on the module. If the charging standard requires 5 volt MCS, that's also generated on the module. So you can actually relatively easily build a DC charging controller that supports all globally available charging standards, and you can just change the standard by exchanging the ChargeBridge module, and then basically also do all combinations. So if you design controller with like 3 ChargeBridge ports, you can have like 1 CCS, 1 MCS, and 1 CHAdeMO if you like, or any other combination of the modules. Yeah, so next slide. So what if you want to try ChargeBridge? We have a couple of reference designs available, both for AC and DC. You can see the AC charger kit here on the left. That's basically a full AC charging port with the relay, the RCD, a ChargeBridge. So that's kind of a satellite front end, but of course you can use it locally as well. All it needs basically is wiring up a network to a Linux computer running EVerest, and you have a charger. The dev kit on the right is basically just wired out all the pins of the ChargeBridge, so you can use this to build a DC charge port or an AC charge port with external relays. And those designs are available on GitHub. They're designed in KiCad. You can just download them, modify them, to build on top of them. But you can also buy those PCBs in our online shop to build a charger within hours, just to play with it. Next slide. Something that's new is there is also an EV side of the ChargeBridge. That's the white module that you can see here. It has all the functionality that the EVSE side has as well, just it has the CP for the EV. And it's not designed for actually be put in a real EV. The use case is more, you can build a desk setup, so you can use 2 development kits, one EV, one EVSE on your desk. You can run 2 EVerest instances, one for EV, one for EVSE, on a single computer or on 2 computers, doesn't matter. And then you can like plug in the charging cable on your desk, and you can actually run a real ISO 15118 session with plug and charge and everything you want. It does Slack, it's like the real protocol. The other quite interesting application of that is, and that's actually what we designed it more for, is for a hill testing setup. So if you're a charging station manufacturer, you can actually plug in this dev kit into your charger all the time. It can be state plugged in, and then like remotely start an EVerest instance that now virtually actually plugs in, runs a charging session, unplugs again. And with this, you can, for example, integrate this directly into the CI. And since it can do WireGuard, it actually can remotely connect from your CI runner container, basically, or virtual machine directly to the ChargeBridge and actually charge do a charging session in hardware there. You still have all the interface forwarding also on the EV side, and that, for example, can be used to control auxiliary devices such as, I don't know, an RFID simulator, like a tag simulator, that's also attached to your charging station directly from the CI. Yeah, so that's basically what we use it for mostly. There is just a little bit of sneak peek. There is also like full production grade controllers coming up for both AC and DC based on ChargeBridge. That's if you don't want to design your own, basically you can use those, but again, those designs will also be available, so you can actually use them as a jump start to design your own controller, saying, okay, I have a fully working controller, I just need, I don't know, another port here and there, or I need the holes for mounting a little bit different. You can just modify that. It will all be available. Next slide. Yeah, so Robert.
Hey, thanks, Cornelius. So yeah, wrapping up, ChargeBridge really brings you faster time to market. You can go from to months instead of years. We've helped customers already with making the first prototypes based on ChargeBridge, and we have something up and running in less than a month. We had a first prototype that was able to charge a vehicle. Yeah, it's not production ready yet, but we really went within a month, have a working board in the field. Yeah, so works out of the box directly with EVerest for 15118 OCP. It greatly reduces the risk for safety certification. So as this is redesigned for safety, we are very convinced that if you use ChargeBridge, you will pass the safety certification in the first go. Yeah, we can't always 100% guarantee because it also relies a bit on what's on the rest of the board. But we are very, very convinced that it's rarely needed to do redesigns, especially if you ask us, like, hey, this is what we're planning to do with it. Hey, can you have a quick look? We can do first time right and get something ready for production. If you want to add additional standards, you want to do an MCS version, as Cornelius already said, it's as easy as switching the ChargeBridge. It's as easy as switching the cable. Yeah, and then maybe adding some power modules, because if you want to switch from CCS to MCS, you might want more power there. But if you would switch from CCS to CHAdeMO, it's a matter of switching the cable, switching ChargeBridge, and the same board can just be used to do CHAdeMO. Yeah, as Cornelius mentioned, you can buy the boards from us, especially if you want to get started for your first trials. That's probably the easiest way to go. And if you then want to develop your own boards because it needs to fit a certain form factor or you need some additional connectors, the hardware designs are available. Makes it super easy to get started and make your own unique charge controller. Yeah, and cost advantages. You don't need to maintain the board support package. It just becomes way simpler. It's way easier to not have to do a lot of the kernel drivers that are needed for the specific embedded I/O. You can just use any Linux, and all those virtual ports show up within Linux, making sure that that really reduces the amount of effort to get those SPI ports, but also means you can buy just a simpler Linux controller to be able to do this. Yeah, and I think what I really love is it's able to reduce a lot of the complex wiring. If you look at that picture here on the right, if you open a lot of charging stations, there are so many cables, and a lot of them, like, we could greatly reduce those cables, and that has a huge advantage. One, in production, it means there's just less copper wire going in. It means less manual work to wire up, connect them. There's less mistakes that can happen with connectors. There's less wear on connectors that could cause issues with corrosion. And it's also, if you need to do maintenance, there's less cables that you could indeed incorrectly connect again. So all of this makes it so much better to make a charging station. We've seen it with a customer. Sorry, we can't show the picture, but we've seen the difference from their first prototypes and the prototype with ChargeBridge. Half of the cabinet is now empty. It looks so amazingly clean. And then, yeah, ChargeBridge and EVerest are match made in heaven. They're designed for each other. ChargeBridge provides all the low-level stuff, all the 61851 CPPP stuff, the PLC communication. If you talk about CCS, the CHAdeMO one, the MCS one will provide Ethernet or CAN bus. It contains all the connectors you need to make a CCS port. You can connect it via single Ethernet or USB to Linux, and then the Linux controller runs EVerest, which does all the high-level communication. So the DIN spec, 1578-2-20, plug and charge. It's Hubjack certified. You get OSP 16 and 201, which for a lot of companies is still like a thing to do, where EVerest already brings you with 2.1 already. It contains all the energy management, over-the-air update. It works with TPMs. So you can securely store all the private keys you need in the charging station, all the stuff you need for plug and charge. It comes with a lot of hardware drivers, so a lot of hardware, the different power modules, power meter, isolation monitors work out of the box. And we see nowadays more and more drivers being added by manufacturers themselves. So it's no longer us at Pionix or other contributors that make charging stations. We really see companies now providing drivers for their hardware within EVerest. And that's amazing to see, because that grows the community, also grows the amount of support for hardware in EVerest. If you want to get started, we have a special offer for you. So if you can buy from us a starter package, which gives you a ChargeBridge dev kit, so the breakout board with a ChargeBridge, plus 20 hours of support from us to get you started with making your own design, getting you up and running. But typically we expect somebody to get up and running themselves, because it's quite easy to just use one of the EVerest demos, hook that up to ChargeBridge with your laptop, and you can quite quickly make something working. And then from there, we can help with requirements, with making plans, debugging stuff, and getting you up and running. So if you want to know, get in touch, QR code on the left, or if you have the slides, click on schedule a session, and Tim or Marcus will have a talk with you. We will do a next webinar next month on the Pionix Virtual Charging Park. So if you want to check if your CPMS scales really well, we have a solution that runs a lot of real EVerest instances in parallel, and do a lot of really interesting testing with that. And that brings us to the Q&A session. For people that haven't found the queue, we have a couple of questions here. If you haven't found it, if you click on the 9 dots on the bottom right, you can go to the Q&A session and enter your question there. First question from Mike. In the DC satellite architecture with central power electronics, is the intention to each ChargeBridge talks to the central power electronics cabinet, or do you envision this working in some other way?
Yeah, there is basically two ways to build this, and both are of course possible. One way is you actually have the full power electronics within the central cabinet, so the AC/DC as well as the DC/DC stage for each port in the cabinet, and then just running individual DC wires to each dispenser. So in that configuration, the ChargeBridge controls the output relay, which typically still sits within the dispenser locally. And the power supplies itself are controlled directly from the Linux. You can still use a ChargeBridge there. I didn't mention this, but there's also a ChargeBridge version that comes without the actual charge function. That means you can also have a cheaper ChargeBridge that's basically just an interface breakout that you can use to have like local CAN buses if you need more of those. Yeah, that's basically one way. Linux controls the power modules within the cabinet, and ChargeBridge controls the final safety relay within the dispenser. And then there is another option that's also sometimes used, is you just have the AC/DC in the central cabinet, but the DC/DC for the individual voltage is still located in the dispenser. This makes the wiring a little bit simpler because you have a DC bus between the dispensers, and you can share the AC/DC load better usually. And in that case, typically the CAN bus of the ChargeBridge talks to the DC/DC at the front and the relay, of course. Yeah, so does that answer your question? Hopefully. Yeah, there was a second question, Mike, from you about sharing power supplies between ports. I think the typical application here is that you have a dual port charger and you have like a stack of modules, and you can basically connect, let's say by default, half are connected left and half are connected right, and then you typically have two relays that can connect the left port together with the right port if one of them is not connected. So this specific scenario is actually supported by ChargeBridge itself. So the Linux still needs to be aware of it, of course, because it needs to plan and announce to the car like how much power is actually available. But the, let's say, safety control of those relays that ensures that you don't do short circuits while two cars are connected, that is actually handled with the two ChargeBridges and like dedicated wires in between. So still the idea here that everything that's safety related is handled by the ChargeBridges, and the Linux basically cannot do a lot wrong here.
Thanks, Cornelius. Then next question by Bill. Has your team helped customers on the vehicle side? The Lumacil IS32CG1112 analog switch is a great IC to manage dual port vehicles. It eliminates the problem that occurs with if two cables are plugged in to a vehicle at the same time. We don't do a lot of projects for vehicle manufacturers. We do support them sometime, but we haven't done real project helping them design their hardware. Then next question. I hope I pronounce this correctly. Prashit. Are your ShareDemo, GBT, and MCS modules currently available on the market? If not, what are your projected release dates? Additionally, could you please provide your estimate monthly delivery capacity and standard lead times? Cornelius, any word on ShareDemo, GBT, and MCS modules when they will be available?
The plan is to have them released by summer. We're currently in testing period with those, but we hope to release them around June-ish.
Thank you. An estimate monthly delivery capacity. If we know in time, I don't think there's the biggest limit is can we get to the amount of components. The rest is up to our partner that manufactures the the charge bridges, and if we know in time, we can ramp up quite far. But indeed, we will get into lead times for components. So if we can plan long enough upfront, I don't see us running into limits there early. But if you want to have more details or certain capacities that you want to know, please schedule something with us, and we can try to understand your request better and see if we can convince you that we were able to keep up with your demand. Then next question from Skylar. Is the virtual failover inside of EVerest would charging sessions see a seamless transition? I think that's regarding to the Proxmox.
Yeah, that's a very good question. So the failover is actually up to now not within EVerest. So what I showed using a Proxmox cluster, this is basically just all the functionality that the Proxmox cluster itself has. And the EVerest basically doesn't notice because it's just running inside of a virtual machine. And the fun part is that the let's say the CAN bus that is in hardware on one side actually like switches physical machines from when transferring the virtual machine, right? Just ends up at another VM. And there's basically two cases. One is if the hardware really completely dies, like you unplug power on one of them, which was running the virtual machine at this moment. Then for the virtual machine, it's like a restart. So the storage, root partition, everything it runs on is actually shared across the cluster. So from a software perspective, this will look like it just reboots. It doesn't notice that it restarts on a different piece of hardware. It just sees, okay, I was rebooting. In this case, basically, EVerest can like restart charging sessions if supported by the car. On AC, this always works. On DC, this works with all the newer ones, but not all of the older ones. So you will see like a short interruption until basically the virtual machine reboots if you like hard unplug one of the computers. Still, the charging part will come back online automatically. If you have the other case where basically the machines are still running, but for example, you do a planned maintenance, I don't know, you want to exchange a fan in one of the computers or so, you can actually manually move the virtual machine from one physical computer to the other one. And in this case, the charging session will actually keep on running. So even if it's a DC ISO 158 session, it will actually continue to charge while the virtual machine is being transferred because both of the hosts are still online. So these are the two cases.
Thanks, Cornelius. Oh, then another name, I hope I pronounced correctly. Joa, is the I/O capacity of ChargeBridge expendable, or is a SoM board needed? We do have a lot of I/O.
Yeah.
I/O extenders, Cornelius?
Exactly. So we have what's typically needed for one charging port. There's also like 10 GPIOs that you can use for everything else per port. So if you have two, it's already 20. If you need more control, you can use like I2C GPIO extended chips. So the ChargeBridge also has an I2C bus to extend like GPIOs and ADCs and things like that locally. That then will also be tunneled through the Linux system.
And another question from Joa. Do you sell or plan production-ready ChargeBridge carrier boards for satellite architectures? At the moment, we don't. But Cornelius showed something, and I think that board would be useful for satellite, correct?
Yeah. So there is things coming up.
Rui, do you already test at least 10 charge bridges controlled by a single Linux board, and do you see any restrictions?
Yeah, so restrictions typically comes with let's say compute power and memory size. So if you have, let's say, a relatively slow ARM board, so if you start at the lowest that we typically see, so let's say a very good old IMX6 ULL, so single core Cortex A7 running at 500 megahertz, so very first generation. It's about the lowest you can usually get in Linux-based chargers. That, for example, will max out at roughly 2 to 3 charging ports. While if you have like a more modern ARM processor, I don't know, Cortex A53 or 55-ish or something, and maybe even the quad core, then it will maybe be 15 or 20-ish or something like that. And then if you move over to x86 platforms, it's let's say more or less unlimited, because even on the cheapest Intel CPU that you can have, it's more like 50 to 100. And if you use like something standard laptop, it's like literally unlimited, more or less. So it depends on how much compute and RAM you have, basically.
And and that's also the reason why to look into these kind of like failover systems. If you really start running a couple of hundreds of sockets on one controller, and if that controller fails, that single point of failure is not something you want to have in the field in that big setup. And that's where you really want to have failover systems available. And if you have 5,000 ports running, and you might want to have 3 servers with maybe even redundant power supplies, because that's a lot. If that goes down, you want to be up and running as quickly as possible. Then we have an anonymous question. Cluster sounds quite expensive. What is the minimum price point and specs for a cluster? And how many charges can you run on a minimum setup?
Yeah, so clusters sound expensive. That's true. It's of course more expensive than an embedded Linux board, but this is like only a viable option for like really large scale installations. So if you think of, let's say, 2,000 chargers in like big parking garage where you want to have 1 outlet per parking port, for example, if you buy like a local Linux system and you invest like 50 euros of BOM cost into having a Linux locally everywhere, that's 100,000 euros for 2,000 chargers, right? So if you compare that cost to a cluster, right? Let's say you buy Intel-based 19-inch rack servers for 1,500 each, and you buy 3 of them, then you have like 4.5K instead of 100K. You buy like a rack, which is another K or something. You can get significantly cheaper than having a lot of individual Linux system at those scales. Of course, it's like not beneficial to have this at 10. And as I said, on the minimal setup, we did this on like really, really cheap Intel N100 CPUs, which is like almost the lowest thing you can get from Intel. And you can buy like a complete small PC for maybe 200 euros or so. And those can already run like 50 to 100-ish. And if you go for, let's say, I don't know, an i7 with 8 cores or so, you can actually run the 2,000 on those, and they're not crazy expensive. You can easily get them for 1.5K or so.
And if you would want to do this, for example, in the bus depot, Cornelis, where we have 10 charges in a bus depot, but we need to know for sure that they would need to come back online, then maybe the cost of running a small N100 might be doable, because it's so important that these sessions are successful.
It also, it's a little bit of a different thinking also, because the moment you cross from, let's say, small embedded Linux boards to running a cluster, this is more like cloud technology, and you can use all the management tools and stuff that you typically use to manage cloud, even though it's local, it's not like on the internet somewhere. And it's completely different from having a really small embedded Linux board, and that also brings some advantages and flexibility in managing these like very large scale installations.
Hey, thanks. Another question. Oh, we still have time also. Rashid, how do we integrate IMDs and temperature sensors into the ChargeBridge? Also, are there specific sensor models you recommend using for this application?
Basically, all the sensors that EVerest supports are supported, because ChargeBridge is just a transparent bridge. So for isolation monitor, it's typically like Bender or Dolt, but there's also others. And yeah, for most of them, there are drivers in EVerest already. Just check the drivers section in EVerest.
Yeah, and if you want to integrate them in ChargeBridge, that means you need to have a driver in EVerest, and you need to wire them up to ChargeBridge. I think that's the most important things you need to do, and the rest works out.
You don't need specific drivers for ChargeBridge. It's just transparent in that way.
Yeah. Question from TH. Do you have a plan to build and sell PLC sniffer tool for V2G?
No, not at
EVerest
this.
is able to do something, isn't it? We can capture.
Yeah, well,
but we can't
EVerest can
sniff.
capture like its own traffic and generate PCAP traces, but that's not completely identical to actually sniffing the wire. And there's no plans at the moment to create such a wire sniffing tool.
But others provide that, I think. I think even
Yeah.
companies like Lumacil have a dev kit that could be used for that. There's other companies that make, they're not even that crazily expensive to have a box that is able that you just wrap around the cable around the charging, a wire around the charging cable, act as an antenna, and just listening in on it, as long as it's not encrypted. Because if with dash 20, as soon as the encryption is up and running, you can sniff the packages.
Yeah.
But that's about it.
Yeah, out of curiosity, I mentioned that it's not mandatory to interface ChargeBridge with EVerest. That's correct. It's actually a separate service. Like there's a ChargeBridge service that you run as a systemd service that basically connects to the ChargeBridge, manages the secure firmware updates of the ChargeBridge and things like that. And basically just that service just creates like local interfaces, virtual interfaces, that then EVerest uses. But you could also use any other charging stack, because in the end, it's just a local PLC device that magically gets transferred to the other side, and it's just a local CAN device that you can use with on the command line with like CANsend or Python or whatever you use. So it's not, it doesn't depend on EVerest. It just fits nicely. And the mapping, how to map the interfaces, that's a little bit more complex. There's a lot of different variations, but in the there's config files for the charge bridges, and you can have like you can give the charge bridges names. That's one possibility via MDNS, and you can just call them like ChargeBridge 0, and then say, okay, everything that's ChargeBridge 0 maps to CAN 0, something like that. So yeah, it's a little bit too much to explain it fully here, but there's multiple ways on how to do this pairing, basically.
Thank you. And then Mike has another question. Is the WireGuard VPN between EVerest controller and ChargeBridge somehow decoupled from the safety certification software? And what's happened if there's some critical CVE that must be addressed?
Yes, so of course that's completely separate. So in the ChargeBridge itself, there's like two execution contexts. It's completely separated in terms of like RAM and flash and interrupt controllers and basically everything. And there is like two different firmwares. There's one safety firmware doing all the safety stuff, and there's a non-safety firmware doing things like the WireGuard and the interface for warning. That's not safety critical. And yeah, the ChargeBridge itself basically has a secure over-the-air update that comes with the ChargeBridge tool, so you won't even notice if you update the ChargeBridge tool. It will also reflash on the next connect all the ChargeBridges.
And we as Pionix maintain, as we should, the firmware for the ChargeBridge.
Yeah.
And then a last question from Kabir. I know the question about price came up last time too. Could you still give a rough price estimate for 500 to 1,000 pieces a year? I think that means, hey, get in touch, talk to our sales guys, and they will be able to tell you, because it also depends on which one. And that is the last question. Oh, there's a new. It says there's a new question. Let's scroll down. Mozen, hope you pronounce it correctly. Hi, thank you for the presentation. I do have two questions. First, do you recommend ChargeBridge EV or 5 for 10 kilowatt charger?
I would recommend using ChargeBridge for everything going forward.
And especially if you do a single port, 5 is a dual port controller. So it might be a bit overkill if you only need a single port 10 kilowatt charger. And then, yeah, it's quite a big board if you only need a single port. And then Rashid asked, can I get the recording? Yes, of course. We will send an email after the webinar. We will publish it as well, and you will get a link to the recording as well. And if that is the last question, then hey, thanks everybody for attending. Thanks, Cornelius, for joining me for the webinar. Oh, there's another last question coming in. Second, have you implemented ChargeBridge car side and control a DC power supply?
So the DC power supply on the car side or on the EVSE side? So on EVSE side, of course, that's all implemented. It's very easy to build like a full charger with power as well. On the car side, it basically behaves the same. It will also switch the relays at the correct moment and everything. What we currently don't have is a driver for a DC sync. So like a battery simulator, but that could be relatively easily added to EVerest.
And we typically run it without.
Yeah, we typically run it without, but it could be like modified. Actually, quite simple to have like also a full closed power system.
Yeah. Then again, thanks everybody for joining. Thanks, Cornelius, for joining me for this webinar, and hope to see a lot of you in the next webinar. As Marco already posted in the chat as well, there's also a SunSpec webinar coming up next week. The SunSpec Alliance is joining EVerest. They are adding they will make sure that the EVerest implementation of SunSpec complies with their requirements. And there's a webinar about that next week. Hey, thanks everybody.